Welcome back to Mr. Morrow's Algebra class. Today we are going to be talking about real numbers and the number line. Once again, it's very important for us to know the vocabulary here because without the vocabulary, we really can't go too far. Well, let's talk about classifying numbers. When you classify numbers using sets, a set is a well-defined collection of objects. Each object is called an element of the set. A subset of a set consists of elements from the given set. You can list the elements of a set within braces. For example, a set of the first 5 odd numbers, 1, 3, 5, 7, and 9. Those are the first 3 odd numbers. Okay, that is a set. Now, there are 1, 2, 3, 4, 5 elements in this set. Within this, we could say, let's form a subset of the first 5 odd numbers larger than 3. Then it would be 5, 7, 9. So the set of the first 5 odd numbers, subset of the first 5 odd numbers larger than 3. Okay, so let's talk about these number sets. The first number set that we're going to talk about, it's very important. It's called rational numbers. And a rational number is any number that you can write in the form of a over b, fraction form, where a and b are integers and b cannot equal 0. You can never have 5 divided by 0. That's called undefined, and it just does not work. So b can never be 0. The denominator can never be 0. Rational numbers include the following subsets: natural numbers, whole numbers, integers, repeating decimals, terminating decimals, and perfect squares. Examples of rational numbers can include -5, which is an integer, 3.775, which is a terminating decimal, 1.53535353, which is a repeating decimal, square root of 49, which is a perfect square, and 3/5, which is a fraction. Now, natural numbers are whole units starting with 1. They're basically our counting numbers. 1, 2, 3, 4, 5, 6, etc., etc., etc. Whole numbers. Whole numbers are the natural numbers including 0. So it's the natural numbers including 0, so they would include 0, 1, 2, 3, 4, etc., etc., etc. Integers. Integers are whole numbers and their opposites. So that would be 0, 1, and -1, 2 and -2, 3 and -3, etc., etc., etc. And the last kind of type of number set that we're going to be talking about in Algebra 1 is irrational numbers. Irrational numbers are numbers that cannot be written as a quotient of 2 integers. In other words, they cannot be written in fraction form. Irrational numbers include the following subsets: non-terminating or repeating decimals. So non-terminating and non-repeating. Non-terminating or non-repeating. For example, pi. Pi goes on forever. This number here, 1.232256556235662, it's not repeating, it's not terminating, so that is irrational. And the second type of irrational number is the non-perfect square, such as square root of 32, square root of 15, square root of 8, square root of 12. None of those are perfect squares. So those are non-perfect squares. That is an irrational number. Now, when we're talking about rational numbers and irrational numbers, square roots came up. And for square roots, Okay, we really got to understand what this means. A number a is a square root of b if a squared equals b. So for example, 7 squared equals 49. So 7 is a square root of 49. Now, we already learned about exponents and powers and bases, so hopefully you can understand square root is when a number is multiplied by itself to give me a product. The square root of 81 is 8. Why? Because 8, I'm sorry, it was 9, my bad. 9 squared equals 81, so the square root of 81 equals 9. Now, there are both perfect square roots and non-perfect square roots. When dealing with non-perfect square roots, you can approximate the value. Okay, so let me explain what that means. If I had a perfect square, like the square root of 81, like I said, it's 9. If I have the square root of 144, that's 12. If I have the square root of 100, that's going to be 10. So those are perfect squares. Now what happens when I have non-perfect squares? Well, remember that this is a radical symbol right here. Okay, this is a radical symbol. This guy right here. And the value inside of the radical is called a radicand. And this is the expression under the radical symbol. That's called the radicand. Now, together the radical symbol and the radical form a radical. The square of an integer is called a perfect square. So if I want to simplify each square root, these are perfect squares. So this is going to work out nice and easy. Square root of 81 is 9 because 9 times 9 is 81. Square root of 225 is 15 because 15 times 15 is 25. Square root of 9 is 3 because 3 times 3 is 9. Square root of 81 over 121. What happens here is we split that up into the square root of 81 over the square root of 121. So the square root of 81 is 9. The square root of 121 is 11. So I have 9 elevenths as my answer. So when you're dealing with perfect squares, it's nice and easy as long as you know your multiplication tables. Now, sometimes you have to work with non-perfect squares. In these situations, you simply approximate the value of the radical as follows. I'm dealing with a square root of 34, okay? I know that is not a perfect square. 36 is a perfect square, but 34 is not a perfect square. So what do I have to do here? Well, let's go ahead. We know that square root of 34 is greater than the perfect square before it, which is the square root of 25. And we also know that the square root of 34 is less than the square root of 36. So 34 is between square root of 25, which is 5, and the square root of 36, which is 6. So it's between 5 and 6. But 34 is closer to 36. So the square root of 34 is approximately, roughly, 6. Okay? So we're going to use an approximation. Depends how close of an approximation I want. If I want an approximation to, let's say, the nearest tenth, then this wouldn't be as easy to do. In this case, you would still know that 34 is closer, the square root of 34 is closer to the square root of 36. So immediately you know it's going to be 5.6 or above, at least 5.5 or above. So how do I figure this out? Well, what I do is as follows. I know that square root of 25 is 5 and the square root of 36 is 6. I know that square root of 34 is closer to the square root of 36. So let's try it's real close, so let's try 3.7. When you go 3.7 to 3.7, it's 9, 4, it's 25, skip a space, 1, 2, 9, 11. You got 9, 6, 3, 1. This is no good because I went 3.7. I don't know what I was thinking there, boys. I am sorry. Should have been 5.7. Sorry. Had a little mess up there. 9, 4. How about we do it the right way now? Okay, so that's 32.49. Okay, not enough. Not enough. I'm going to need more. Okay, so let's go ahead and try 5.8 times 5.8. When I go 5.8 times 5.8, that gives me 33.64. Let's try 5.9 times 5.9. 5.9 times 5.9 is going to give me 34.81. So who's closer to 34? 34.81 or 33.64? 33.64. So this is roughly 5.8. Depends what they want. If they want you to approximate it to the nearest whole number, nice and easy. If they want you to approximate it to the nearest tenth, then you gotta go a little bit tougher. Okay, let's try a little bit more of a difficult one. What if I want you to figure out the square root of 386? Well, the square root of 386. What's going to happen here? Well, the first square root smaller than that is the square root of 361, which is equal to 19. And the perfect square larger than that is square root of 400, which is 20. So I know that the square root of 386 is between 19 and 20. Is it closer to 361 or 400? Well, I'm 25 away from 361, and I am 14 away from square root of 400. So roughly, square root of 386 is approximately 20. And I hope that makes sense. Okay, now, inequalities. An inequality is a mathematical sentence that compares the value of two expressions using an inequality symbol. And the symbols are as follows. Is less than, got less than. Is greater than, it's greater than. Is less than or equal to, that little piece right there means that it's also equal to. And then, of course, is greater than or equal to, again, has that little line underneath the inequality symbol to represent that it's also equal to. Now, if I want to compare radical 17 and 4 1/3, I'm going to compare them using inequalities. Well, 17, square root of 17, okay, let's see. The smallest perfect square is square root of 16. The one larger than that is 25. So here I know that the square root of 17 is between 4 and 5. But it's real close to the 4. So I'm going to go ahead and try 4.1 times 4.1. That's 16.81, pretty close. Let's try 4.2. That's 17.64. 16.81 is closer. So we can say easily that the square root of 17 is roughly about 4.1. 4 1/3, though, is equal to 4.33 repeating. So very easily, 4/3 is greater. So you would write it as square root of 17 is less than 4 1/3. You always read from left to right. And that's it. So I hope you guys enjoyed this lesson. Hope you learned a lot. And I will see you in class. Thank you. Bye-bye.